So I'll try to share my screen right now. And this one, okay. Enrico, can you see my screen?
Yes, yes. You are already in the YouTube, so you can begin.
Okay, so this presentation addresses the latest development about GBus GAST-F ionosphere impact using the prototype module GBus Messenger. With the latest update I've been doing and analyzing, thanks also to the research team of Professor Galera at University of Unesp. So the main agenda for is the description of Pegasus, what is Pegasus and its objectives. We will see some GBus fundamental and current implementation status, notably for GBus dual frequency multi-constellation. We will see GBus messenger objectives, updates of latest version, and the analysis of GAST-F under ionosphere irregularity effects, and then some conclusions. So Pegasus essentially is a software for GNSS data processing in flight and on the ground using algorithms that they are issued in the from RTCA, ICAO, Eurocarb, and yes, and the ICAO SARPs. Those are identified as minimum operational performance standards for GPS Galileo standalone, and notably with augmentation SBus, GBus, and advanced RAIN nowadays too, on which we are working. So Pegasus includes standardized graphical representation of the results that we have been able to develop thanks to the feedback of Pegasus users like you are or you will be in the next few days. And it uses reference GNSS processing by many organizations. Thanks to your feedback and the feedback of all around the world Pegasus users from SBus and GBus world, we have lots of feedback that helps us to leverage Pegasus to a well-verified, validated tool using different type of data and addressing different varying of needs. So Pegasus has contributed mainly to the validation of European SBus EGNOS in 2010, and nowadays we contribute to the validation of GBus GAST-D, means GBus Cat2-3, and notably the development of GBus for DF dual frequency multi-constellation. So the objective is education of aviation service provider and regulators, validation of aviation standards, support state campaign to validate GNSS performance, and enable exchange of comparable results for faster accumulation, as well as verification of augmentation system performance. And Pegasus, mainly the objective is to be independent from manufacturer and service provider. And the latest objective is to evolve the tool to support GBus and SBus, especially CESAR research activity, where CESAR is the Single European Sky Air Traffic Management Research Program. It's the European one. So we do evolve Pegasus in live due course of the project in the CESAR. So Pegasus essentially provide, as already mentioned, processing according to published standards, simplified automated processing, scheduling of processing, traceability of the parameters, and the most important characteristic is the modular analysis and open interface and standardization of process of analyzing the data of Pegasus, especially the modularity. Modularity, it means to adapt to several scenarios that a researcher, a manufacturer, air navigation service provider could face to analyze the GNSS performance at his premises, in his laboratories, or just in the classroom of the university. We do provide support to the users with varying needs on different GNSS systems that they are supported by Pegasus, and especially full documentation and tutorials are provided, and as well as training courses that we provide in Eurocontrol Institute of Navigation of Air Navigation Services. So The Pegasus, in a nutshell, Pegasus, it's a modular tool. So we do provide a tool set of modules on the airborne and ground side to be interfaced and interoperable between them, adapting to the scenario of processing. For example, for GBus, we do have modules for the processing from real GBus station, as well as for simulating a GBus station for all category of services, as well as to provide services concerning the validation of the characteristics of GBus station installed in an airport, or doing a quality analysis of the signal in space of GBus simulated station and the sighting requirement of GBus. Concerning the onboard, it's exactly the same. We can process static and dynamic data with a receiver on the ground, or an airborne receiver like a multimode receiver, classical one that is equipping aircraft today. And then we can download the data, convert the data, analyze it for static or, for example, dynamics, and etc. So we do those services for GBus mainly, and then SBus and RAIM and IRAIM in the next future. Here we have the general view of the Pegasus user community, or the international users we do have. They do comprise universities, public and private research institute, industries, manufacturers, and especially air navigation service provider and regulators and international agencies like the ESA, for example, the FAA, are the ones involved in the GNSS performance analysis, which provide us continuous feedback to improve Pegasus and compare especially Pegasus versus the results of their independent tools, which leverage Pegasus to worldwide recognize the tool reference for GNSS performance analysis and assessment. Concerning the GBus, we find lots of time the term GAST. GAST stands for GBus Approach Service Type, which refer essentially to the performance criteria of precision approach in an airport. So Pegasus nowadays support services between GAST-C and GAST-F. GAST-C is GBus Cat1, is a single frequency GPS, and GAST-F and GAST-E are not yet standardized. Those are just CESAR specific research program in Europe, and actually the proposed mode GAST-E and the GAST-F are just included in Pegasus design justification documents that you could have if you ask for Pegasus installation on your computer. You will have also the documentation describing those two last modes, the dual frequency multi-constellation, even GAST-CD are very well known a standardized mode of GBus for Cat1 and Cat2-3, which SARPs are now published for GAST-D as well since December 2018. So this is this picture is a picture from FlyGLSnet, which take care the LATO Group International GBus Working Group, which gives us the actual status of development and deployment of GBus station. Notably, we have to have a look for light green and dark green of dots everywhere on the countries in the world for operational GAST-C, for national and private use, and the dark green especially for GAST-C operational ICAO station. So the GAST-D, it's just a research implementation, advanced status of research implementation and extended scope, but no yet certification has been reached about the GAST-D station. So Eurocontrol provides support to the stakeholders of GBus, managing two main working groups. Those are the LATO groups, stand for Landing and Takeoff Focus Group, that take place in Europe at least 2 times per year, and as well as the co-chaired with the FAA in US, the International GBus Working Group that take place at least once per year one time in Europe, another time generally outside Europe, can be US, North Hemisphere or South Hemisphere, etc. So now we come to the core of my presentation, the GBus Messenger. GBus Messenger is a module of Pegasus toolset that enables the Pegasus user to simulate GBus station, starting from data collected from reference receivers, and which objectives are mainly rewrite the GBus Mars 3 ground modules. Those are the old modules of Pegasus that they were providing only GAST CD, but now the objective was to rewrite those modules, generate GBus correction and compute accuracy prediction, to update GAST CD to the new standard, as well as to the specification of CESAR project for GAST-F specification. So the opportunity to rewrite those modules gives us finally the opportunity to perform a qualitative analysis and citing constraints ability for the Pegasus users to analyze citing requirements such as multipath and ionosphere. The third objective is to make available a series of qualitative output parameters that they are helpful to the Pegasus users, but cannot be used as a significant information to fully characterize the multipath and ionosphere due to the possible experimental installation limitation. We think about the quality of the receivers, antenna installations, multipath mitigation that can take. So it's just experimental installation, and then the objective is to let the Pegasus user familiarize with the GBus data, process it to understand, learn, and build up his knowledge with. So it's just a qualitative analysis. And the last objective is GBus Messenger is not committed essentially to the verification of GBus error model, because essentially the GBus Messenger implement the standards, as I said on these slides, that they are very well stated in EuroCai document 114, as well as RTCA MOPS standard ICD for its interface control document for GBus station 246E, and GAST-F specification. So the simulated station is a minimum operational performance standard station, which does not implement any other monitor outside as specified in those documentation and Pegasus design justification documents that we are developing thanks to the CESAR project partners, where also GBus manufacturers, European ones, are participating in. So the VDB message specifications that we got in are compliant for GAST CD current prototype and operational certified stations. Those are specified also in document 246E for L1E1 VDB data. And the newest messages, such as message type 42 and 50, those are compliant to CESAR specification actually for L5, E5A, notably for GPS and Galileo ones. So the differential correction and Iono information message contents are generated using the currently available navigation message, notably for message type 1 and 11 with 130 seconds smoothed. We do use GPS legacy navigation message and Galileo iNav. But for message type 42, due to the lack of standardization of RINEX format for CNAV, for GPS L5, we use the LNAV at the place of CNAV. So we have already an approximation here. And of course, for Galileo, on L5, we use the FNAV. For message type 50 in GBus Messenger, we don't have yet information regarding the ionosphere, since message type 50 was is intended for high rate satellite integrity information update on board the aircraft, and actually we do use it just to flag if corrections are available for that satellite. So it would be nice in the next future to have also your feedback about the development of that message for update of ionospheric information usage for satellite. So the novelty of GBus Messenger, it's not only to implement GAST CD latest standard and GAST-F messages for dual frequency multi-constellation. It's the ability to provide ranging information for each reference receiver. Lots of information is provided in the ranging files for each reference receiver, such as multipath, ionosphere, pseudo-range correction, range rate corrections, and B values. Those are the candidate values. It means those are the candidate reference receiver station monitoring unit parameters that after are used by the central unit of the GBA station to form the messages. And this is quite helpful because those are not submitted to quantization that happen to the broadcast messages. So we don't lose information, especially in that part of the data. So we do implement also code carrier divergence, multipath estimation, and code minus carrier divergence free. As you see in red, those are inactive monitors. This means they don't act on the generation of the messages, the content of messages, differential correction and integrity, but those are there just to provide as a useful index of the effects about the ionosphere, multipath, and code minus carrier, of course, divergence free for multipath impact. Concerning the ionosphere monitoring parameters, this is the latest update which we were referring to in the title of this presentation. We do implement the guidelines for ionosphere monitoring that they are issued in the context of APAC, of ICAO, Ionosphere Study Task Force Group, and do we implement the parameters like amplitude, scintillation, rate of change of total electron content, and sigma code carrier divergence as specified in the document of the ICAO, since Eurocontrol is committed to safeguard and assure the safety of air navigation. So we do refer especially to the ICAO documentations to be also interoperable data between air navigation service provider that they are submitted to different regulations of their state regulators. And concerning the ionosphere gradient estimation, we do propose the implementation of dual frequency time step method. The idea essentially of GBAS messenger consists as to use each reference receiver of a simulated GBAS station as a, let's say, a nano or micro ionosphere monitoring system using the time step method. Time step, it means to use, to estimate, the ionosphere delay at two different time T1 and T2 using dual frequency carrier phase, dual frequency linear combinations of those in two time instant different. So if we use dual frequency, we do have an estimation of ionosphere delay that is quasi, let's say, unbiased, because common bias between the same satellite and the receiver at the time 1 and time 2 are the same. So those can be eliminated when we do differentiation. The problem is the fact that the distance between the ionosphere pierce point differ in function of delta time that we choose. And during this delta time, the ionosphere can change. So the estimated iono gradient is essentially a mixture of time and spatial decorrelation. But since dual frequency linear combination is timely independent, this makes essentially the estimated iono gradient independent from the length of the baseline, because for a fixed time interval of sampling, the baseline, the distance on the ionosphere thin shell between two ionosphere pierce point is a function of the speed, relative speed of the satellite with respect to the receiver. So this means that at a low elevation angle, we have longer baseline, and closer to zenith, we have the shorter baseline. So the idea here for GBAS messenger is to set up a configuration for the station in such a way each reference receiver can do estimation of a ionosphere gradient using different time sampling. So the challenge is to choose the right time sampling to have separation distances that are interesting for GBUS. This means all the separation distance that they are between, let's say 0 for GBUS reference point until the range of the GBUS station. So the range of EDB messages, it's about 24 nautical miles that translate more or less in 41 or 42 kilometers. So delta T has to be chosen accordingly to this distance because the spatial decorrelation maximum is 42. So the validation and verification activities that we have done for GBUS Messenger, we have used the data from a real GBUS station, a prototype GBUS station, but this is only internal verification. You can understand for the confidentiality of data of GBUS users and manufacturers with Eurocontrol. And then the interoperability of the tool versus, of course, Pegasus module that they are largely used in GBUS world to convert the data, analyze the position solution on board the aircraft, and the old modules for the generation of correction and multipath analysis. Of course, the most important feedback we have nowadays is thanks to the help of Professor Galera of the UNESCO University and his research team for the validation and verification of the results of GBUS Messenger, notably for the parameters, using actually the SMR query tool and their exceptional experience of which I'm profiting. So here I propose the results for the simulated GBUS station at UNESCO Campus University, where we do have 4 receivers. Those are 4 receivers that are laboratory receivers commonly present on the market and using choke ring antennas. So of this simulated station, we have 3 reference receivers and a simulated airborne receiver that is static. Over here, we have a serious limitation, notably the fact that the airborne receiver is very close to the GBUS station. So the analysis of GBUS affected by ionosphere, it's quite challenging because we have the maximum spatial decorrelation, it's around a kilometer, let's say a kilometer from the GBUS reference point. So this is the first. And the second one, concerning the airborne ionosphere residual model of uncertainty, we have a limitation, the fact that our airborne receiver stand on the ground and then it's affected by the multipath and noise background that is present over there due to, unfortunately, the limitation we have in the installation of the antenna, and especially for the fact that the receiver is static. So we are going to essentially underbound the ionosphere residual model in that case. So notably, even we have those limitations. On the right, I do present the GAD plot. GAD stands for GBUS Accuracy Designator Plot, which shows us the quality of GBUS station simulated at university, where here you can see essentially the influence of multipath at low elevation angle, where it stands until 30 degrees, and then it lowers down until the zenith for the L1 100 at 30 seconds smoothed and for the L5 measurement. So now I do present you just the results of the dual frequency time step method for the 3 reference receiver, which idea is to sample the ionosphere at 1 minute, 35 seconds, and 15 seconds. So those are the 3 reference receiver of our GBUS station. And then you can see that passing from 60 seconds to 15 seconds, the baseline that we can scan up the head of the receiver range from, let's say, maximum of 30 kilometers to 10 kilometers. But at the same time, you can see that passing from 1 minute to 15 seconds of the receiver that they are scanning the sky at the same time during the same day of data where no ionosphere was present, we can see that the residual biases, they become worse as the baseline, they are shorter for shorter time sampling. This is just the fact that the iono gradient is a ratio between the differential iono at 2 different instants. divided by baseline. Becoming shorter the baseline, higher is the results, let's say. So we do increase the spatial temporal decorrelation of our estimated error in the essentially the ionosphere gradient, or let's say the ionosphere anomaly. Here I do present for the same reference receiver another day where the ionosphere was active and what I have been able to detect. So we can see that essentially passing from 1 minute of scanning to 15 seconds from the PRU2 reference receivers to DMC1, we have essentially for an entire day of data, a sigma vig that change of 1 millimeters per kilometers, essentially. This is for this particular day. So when I did present those results to my colleague, they said, essentially, this is multipath or noise. So my challenge was to demonstrate that this was detected at least when satellites were above 30 degrees elevation angle that you can spot from the dot circles here that identify the 30 degrees elevation angle. On the left side, we have active ionosphere, and on the right side, we have quiet ionosphere representing the ionogradient as estimated one. We can see that for a quiet ionosphere, we have more or less, let's say, a monochromatic color, but here we can just spot for few satellites something. So there is effectively a change. But to better understand this one, we did compute for the same days the correspondent ROTI, the rate of change or total electro content index. And then we can see, especially for the active ionosphere, that at least for 2 or 3 satellites, we have effectively a change for the ionosphere delay indicated by the ROTI. But essentially for the quiet ionosphere, we can see that below 30 degrees, the change of the ROTI index, it's mostly due to multipath, the strong multipath and background noise that we are suffering with. So concerning the detection of those ionosphere irregularities, I just tried to isolate which satellites have impacted by the higher ionosphere irregularities. So here I have filtered in function of time. This is this is UTC time, of course. The local time, it's UTC minus 3 hours. So it's more or less between 9 o'clock in the evening and 11:30 in the evening. Or what's happening for gradients that they are bigger than, as estimated, 100 millimeters per kilometers. So in function of the time interval, I did detect for those gradients that I could see in function of time, I have filtered the sky plot function of time, which were the satellites that they were, let's say, used to scan the upper head reference receiver sky that can be seen. In that case, we can see at least 3 or 4 satellites. And then I invite you to see something. Even the trace, let's say the ionosphere pierce point, they show that those satellites, they were north-south. We can see that the impact effectively does as you would expect, being you in an equatorial region, this should be on the axis east-west. So we see effectively that this is impacting all the satellite for north-south on that direction. So something come back saying, okay, this could be effectively a ionogradient or scintillation, but let's see what it is. So for those satellite, PRN Galileo 106 and GPS 27 and 8, I did show just in function of elevation angle, the ionogradient estimated one and the rate of change of total electron content index. And then we can see that those estimations are well above 30 degrees. Here, there is something important to state that only the PRN 27 is a rising satellite. So the elevation angle is increasing from 30 to 70, and PRN 8 and 106, those they go setting. So the elevation is going from higher to lower one. So here, even those are going lower, I need to stop to 25 degrees elevation and 50, but after all, there is a strong multipath for those ones. At least for the PRN27 that is showing the, let's say, the stronger estimated ROTI index, I did want to analyze, for example, for the reference receiver DMC1 of our simulated station, what happened regarding the GNSS measurements and the candidate pseudo-range and p-value corrections for my GBAS station. So essentially on the first line, we see for L1, L5 measurements of the satellites, the fading of code to noise ratio, and then shadowing and fading again. That's something that would tell to myself that I'm not very much ionosphere expert. This would be scintillation. And then I tried to correlate this information with local information such as code minus carrier to be sure that it's not multipath. We can see that this stand between its maximum, it's a meter in absolute value. And then the parameters for ionosphere monitoring as suggested by the ICAO APAC Ionosphere Study Task Force Group, the sigma code carrier divergence meters per minute. Then we can see the correlation with the highest fading of the code to noise ratio. And then something here, the S4 estimated, unfortunately, it's just an accessory parameter because we are using data at 2 Hertz. So this is just as an indication for the user, but for the next future, we foresee to include also a scintillation receiver as a reference receiver for the GBAS station. What I'm showing here, it has been analyzed and verified thanks to the help of the research team of Professor Galera, comparing my S4 estimated for L1, L5, 2 Hertz with 50 Hertz estimated by ISMR query tool. And then we found sincerely an astonishing, let's say, behavior, strong correlation between both. But I believe here I've been very much fortunate because we have low frequency of the band scintillation over here, and then to get the S4 very much correlated between GBAS messenger and ISMR query tool. So the last 2 lines, they show the B values and the first order derivative of pseudo range corrections, which show in correspondence of the bigger fading of code to noise ratio, they do show essentially some additional noise as expected. But here the oscillation that you can see on the pseudo range correction first order derivative, it's not due to the ionosphere, luckily, but this is due to the clock offset management of the receiver that is contributing for the computation of the correction. So this is the clock offset, since those informations are not yet clock adjusted. So those are just the candidate value. So then we can see the effect of the estimated ionosphere irregularities or effects, function of time for the ROTI, and what happened on the parameters of the messages, notably message type 1, 11, and 42, for the 3 satellites affected by the strongest ionosphere. And then we can see that highest noise on the range rate correction parameter is higher than the range rate correction for the other 2 satellites, the blue and the green one. So why I did choose to show those parameters? Because the range rate correction, it's the most, it's the best parameter one to show, since sigma pseudo range ground and B values are submitted to quantization and elevation bin. So those are binned for elevation angle, so statistics occur, and quantization occur for the construction of messages before transmission. So noise disappears. So this is the only parameter I found that show clearly the effects of the ionosphere irregularities on this one. So finally, I'll have to present the last 2 slides. I don't take more than my minutes. I see I'm a bit late. Sorry, Eurico. and all the audience. So here I showed for using Pegasus, the module for the airborne receiver, the GASTF mode that is called single frequency using dual frequency ionosphere monitor. This means that only dual frequency satellites are used, the GPS and the Galileo, to estimate and monitor the ionosphere, but single frequency position solution that is used to estimate position error and protection level. So in that case, we see that protection levels both on the left and right side of the pictures here of the slides well bound the position error, even at the end of the time interval when ionosphere irregularities have been detected. Here we can see that vertical protection level that is more sensitive to the geometry using and to the noise present approach the position error. This I can justify thanks to the fact, as I said, the PRN 106 and PRN 8, they are descending and they do contribute quite much with multipath at a low elevation angle that is compressed between here, it's between 10 and 15. So here I had even, of course, to elevate a little bit the masking angle, passing from 5 to 7 degrees, because we have lots of multipath in there. So as a last slide, we have the GASTF. It's the iono-free combination. And also in this case, we can see effectively that protection level well bound the position error, but you can see immediately that position error here doesn't jump like in the case of single frequency, but is noisier due to the interfrequency bias, the square ratio of the two frequency L1, L5, because here we use linear combination of the frequencies. And another element that you can spot is the slightly difference. I go back, and here you can see the slightly difference between the number of used satellites, and this is due to the airborne signal quality monitor that triggers for few satellites, notably for 106 and 8, that they are sometimes excluded by position solution due to the multipath and noise present on the measurement. So I'm done. I finished my presentation, and I didn't write really the conclusion, sorry. So the conclusion is the objective was just to correlate what an ionosphere irregularities can impact on the GBAS corrections, both on the ground and the airborne side. Then for the next future, we foresee just the validation and verification activity, notably with the UNESCO universities and all colleagues participating in their research activities, as well as with the Boeing Technical Center. So I'm okay with my presentation. Thank you for your attention. And if you have any question, you are welcome.
Thank you, Natalie. We will have time for just two questions, please.
Yes, I try to show the, I don't know, I am in Portuguese. Oh, yes, right. I'm ready for question. Thank you.
Please, if you have questions to Natalie. Okay. It's an excellent presentation. Thanks so much.
Oh, thank you very much. Thanks to you for the great opportunity. And thanks for the audience.
Thanks to all speakers and to all participants. And this was a high-level presentation. Excellent.